Have you ever wondered what's really going on inside your microwave when you hit that start button? Or, how the gas pump knows exactly which grade of fuel you selected? Well, there's this hidden language at work, a really simple set of commands that brings all these devices to life. And today, we're going to decode that language.
So how do you tell a little piece of silicon, a chip that's smaller than your thumbnail, what to do? How does it end up controlling a whole machine? That's the big question we're going to tackle.
Well, the answer is a microcontroller, like this one right here, the legendary 8051. You can think of it as the brain of the device. And, just like any brain, it needs a language to understand things. For a chip, that language is called an instruction set, which is just a fancy way of saying it has a very small, very specific vocabulary of commands it knows how to follow.
So, here's how we're going to break this down. First, we'll see how a chip handles its most basic resource, data. Then we'll get into how it actually flips the switches to talk to the real world. After that, we'll see how it gets smart and makes decisions. And finally, we'll put it all together to see these commands in action. Let's get into it.
All right, first up, moving data around. Look, before a chip can do anything clever, it has to be able to shuffle information from one place to another. These data transfer instructions, they're the absolute foundation for everything else that follows.
The most fundamental command, the one you'll see everywhere, is MOV, which is short for move. Think of this as learning the basic nouns of the 8051's language. It's how we copy data around inside the chip or just load a specific value into a little temporary storage spot called a register.
Let me show you how it works in practice. A command like MOV A, #55H tells the chip, hey, take the value 55 and stick it in this special spot called the A register, which is also known as the accumulator. Now that little pound sign, the hashtag, is absolutely crucial here. It tells the chip to use the number 55 itself, not to go looking for whatever data is at memory address 55. A tiny symbol, but it totally changes the meaning.
And what's really cool is that move has a couple of specialized cousins. You've got MOVC, the C is for code, and it pulls data from the chip's permanent memory, its ROM. Think of it like reading from a printed manual that never changes. Then there's MOVX, for external, which is how the chip talks to extra memory or other gadgets connected to it. Each one is a specific tool for a specific job.
So now our chip can move data around inside its own head. That's great. But the real magic, the whole point of this thing, happens when it starts interacting with the outside world. And that brings us to our next section, flipping the switches.
This right here is what made the 8051 such a game changer back in the day. It has the ability to control individual pins, single electrical connections. Instead of having to change a whole group of 8 at once, it has the precision to control just one. And that's exactly what you need to do things like turn on a single light, read a single button press, or control one specific part of a machine. And the commands for this are about as direct as you can get. Set B stands for set bit. It just turns a pin on by sending it a high voltage. And CLR stands for clear. It turns the pin off by sending it a low voltage. Set B P1.0, click, the light's on. CLR P1.0, click, the light's off. It's just beautifully simple.
And then you've got this handy one, CPL, which stands for complement. This is pretty much just the flip command. So instead of having to check if a light is already on before you turn it off, you can just tell it to CPL, and it'll instantly flip to the opposite state. Perfect for things like making an LED blink.
Okay, so our chip can move data around, and it can flip switches, but right now, it's just following a script, one line after the other. To make it truly smart, it needs to be able to make decisions. And that brings us to section 3, logic and decision-making. This is where the code starts to feel, well, intelligent. Instead of just running line 1, then 2, then 3 in a boring sequence, branching instructions let the program jump to a totally different part of the code if a certain condition is met. This is the secret sauce for creating loops that repeat tasks or for making a device that actually responds to what's happening around it.
The absolute workhorse for creating loops is a command called DJNZ, and the name tells you exactly what it does. Decrement and jump if not 0. It's simple. You start with a number in a register, this command subtracts 1, and as long as that number isn't 0 yet, it jumps back to an earlier spot in the code. This is the classic, old-school way to create a simple pause or a time delay.
Okay, let's just trace the path on the screen here. It's not as complex as it looks, I promise. First, we load the number 200 into a register, R5. Think of that as setting a countdown timer.
Next, we have a label called here, which is basically just a bookmark for the start of our loop. The instruction DJNZ R5 here does two things. It subtracts 1 from R5, and if the result isn't 0, it follows that arrow and jumps right back to here. It'll do that 200 times until R5 finally hits 0. At that point, the loop breaks and the program just moves on. We've just made the chip wait.
Now, for making actual choices, there's CJNE. It means compare and jump if not equal. This is pretty much the 8051's version of an if-then statement. It compares two values, and if they don't match, the program can jump to a completely different set of instructions to handle that specific situation.
So let's see this in action. Imagine a button is connected to one of the chip's pins. We can use a command like JNB, which means jump if bit is not set, or in plain English, jump if the button isn't being pressed. The code will just keep checking the pin, seeing it's low, and jumping back on itself, just waiting. The second you press that button, the pin goes high, the condition isn't true anymore, and the program breaks out of the loop and moves on. That's how you make something responsive.
So, we've got our building blocks, right? Moving data, flipping switches, and making decisions. Now for the fun part. Section 4 is all about putting it together to see these simple commands do something useful. Here's a classic example, sending the letter H to another device. First, you see a data transfer command. We move the code for the letter H into a register. Then another move puts that data into a special spot called the serial buffer, getting it ready to send. And finally, a bit control command. We set B to turn on the timer that controls the speed. See? Data transfer and bit control, all working together to get one specific job done.
And this is really the most important thing to get. The entire complex world of electronics around us, I mean, from a simple coffee maker to a massive industrial robot, is built from a clever combination of these incredibly simple commands. It's not about having a huge vocabulary, it's about using a small one with a lot of creativity.
So next time you use remote control or adjust your thermostat, just remember what's going on under the hood. There's a tiny brain in there, speaking a simple language, building a whole world of functionality from just a handful of commands. So what device near you right now do you think is running on a language just like this one?